Today we're going to talk more about probability. Last class we said what probability was. Now we're going to talk about some ways that we can compute probabilities and some things that we can do probabilities. On the study guide, I think I refer to this as intermediate probability. So there could be an advanced probability, but you won't get the advanced probability in this class. The advanced probability you can save for graduate school or an advanced statistics class. So this is probability beyond the basics. Today we'll talk about events, we'll talk about complements, mutual exclusivity, conditional probability, independence, joint probability, permutations, and combinations. So an event. Remember last time we talked about statistical experiments, and we said, like, a statistical experiment is a well-defined procedure that results in some outcome. An event is just a set of one or more outcomes. So if we flip a coin 5 times, we have 5 outcomes that each comprise, or that together comprise an event. Does that make sense? So an event is just a subset or a set of the outcome space. A single outcome is often referred to as a simple event. So today we'll talk about the following types of events and their probabilities. One outcome or another outcome. For example, a heads or a tails. What's the probability of a heads or a tails? Anyone know? 0.5? No. 100%, which in probability we would say it's 1. Probability is 1. One outcome and another outcome. Psychology major and female. I'm guessing the probability of that would be fairly high. We don't have 100% females in the department, but we have a lot, as is typical in most psychology departments around the world. How about for heads and tails? What's the probability of getting a heads and a tails in one flip? 0. Good. Alright, so when we talk about probabilities, a useful tool is a Venn diagram. A Venn diagram is basically a pictorial representation of outcome space and the events that can occur in it. So different events are represented as different regions in the diagram. Overlap of different regions reveals relationships between different events. This is complex, but we'll get to an example in just a minute. If there's a bounding rectangle, that's going to represent all of the conceivable outcomes that could occur. So in the previous class, we talked about the outcome space for heads and tails, and I had this rectangle, and then there were 2 squares on the inside. So that big bounding rectangle, that's the entire outcome space. And then those individual regions, those represent different outcomes or different events. Those would have been simple events. If we don't have a rectangle, then the total surface area of all of the things inside of that Venn diagram are going to represent the outcome space. So this is just a joke. So don't get angry. Alright, so there are cool people, and there are smart people. There are some cool people that are also smart, right? We also have hardworking people. We've got some cool people that are hardworking, and smart people that are hardworking, and we've got some people that are cool, smart, and hardworking. So we can talk about these different spaces differently. It's possible that the cool and smart people, these are sociology majors, right? Cool, smart, gotta be smart to be in sociology. How about smart and hardworking? What's a major that's smart and hardworking? Law, medicine. I put engineering. They're smart and hardworking, but they're not cool. Right? Alright, how about cool and hardworking? I don't know. Business? When I went in the States, like the business students, they like to party and have fun, but they're hardworking. Maybe not as smart as the engineers. And then in the middle, what do we have? That's right. Okay, so there's no bounding rectangle. So this space represented, the surface area of all 3 of these circles would represent all the types of people that you could potentially observe. And then we have overlap that shows us relationships about these different types of people. Okay, so back to our good old coin. So probability of heads is 0.5. Probability of not heads is 0.5. Probability of not heads is just the probability of a tails, which if it's a fair coin, I maybe should have said good old fair coin up there. Probability of not heads is also a 0.5. Another way to get the probability of not heads is using axiom 2. So I had some trouble describing what an axiom was last time, so we Googled it after class. And basically, an axiom is a statement that is generally accepted to be true. So it's like a law, sort of what I was suggesting. All right, so the axiom 2, it said the probability of all simple events must add to 1. If we have an event heads, an event not heads, that's all of the possibilities, right? There are no other possibilities. So those two things must add up to 1. So what we could do is take 1, subtract the probability of heads from that, which is 0.5, to get 0.5 of not heads. So we could do this if we didn't automatically intuit that probability of not heads here would also be 5. Now, heads and not heads, these are known as complementary events. They complement one another. So, like, if you think about complementary angles in trigonometry, what do complementary angles do?
120 and 60.
120 and 60, right? Complementary angles add up to 180. So complement, you can think of it's something that's going to add up to a whole thing. In terms of angles, we have a whole switch of direction. There are 1O types of people, those who know binary and those who don't. You guys get this? 1O is binary for 2. Not very funny. Okay, so it's not that there are 10 types of people, there are 2 types of people. But I've written 2 in binary. So if you knew binary, this was funny. If you didn't know binary, maybe not so much. Anyway, this is complementary. I know binary. She looks like she knows binary. The rest of you maybe don't. So there are those who know binary and those who don't. Those are complementary. We talk about other types of people. Psych majors and non-psych majors. Are these complementary or not?
Yes.
Yes, they're complementary. If we assume that you can't double major or anything like that, and there are psych majors and then there are non-psych majors, that describes everybody. So complementary events describe the whole outcome space, the whole event space. How about psych majors and history majors? Are these complementary? No, because there are also sociology majors and engineering majors and the fun, hard-working business people too. All right, so let's do some Venn diagrams to look at complementary events. So the complementary events, they're going to fill the entire space and represent every possibility. So with the coin flips, so the entire space of coin flips is like this. Half of them are heads, half of them are not heads. These are complementary events. Here we don't have a bounding rectangle, so the entire event space is indicated by the total surface area of the different regions. So here we have psych and not psych. Are those complementary? Yes, there's nothing else over here. If there was a psych and not psych, then that would mean that those would not be complementary. But the way I have them there, that is complementary. Okay, so mutual exclusivity is when 2 events cannot co-occur. You can't observe the 2 things at the same time. So what's an example of mutually exclusive events? Mutually exclusive outcomes.
Day and night.
Day and night, right? It's day or it's night. It can't be day and night. Actually, some people back hundreds of years ago, they would freak out occasionally because they thought it was night during the day. Why? Yeah, eclipses. But we know now what an eclipse is, so we would say that the eclipse still is day if it's day and it's still night if it's night, right? So complementary events are mutually exclusive. You can't have a psych major and a not psych major if we assume that there's no double major, right? Some complementary events are mutually exclusive. So some non-complementary events are mutually exclusive. So psych majors and history majors we said that these are not complementary. Together, the psych majors and the history majors don't make up all of the majors. But if we assume that you can't double majors, they are mutually exclusive, right? You're either a psych major or you're a history major. You're not both. Some non-complementary events are not mutually exclusive. So we could talk about getting two outcomes. We're going to take a person, and we're going to ask them their major. What's your major? Psychology? Are you male or female? Sure. Okay. He's a psychology major and he's male. Are those mutually exclusive? No. Why? Because they can co-occur. We can have psych majors that are female. We can have history majors that are male, right? We can't have a heads and a tails, but we could have a heads of 1 lira. We could have a heads of Bashkarush, right? So we could look not only at whether it's heads or tails, but the value of that thing as well. So some non-complementary events are not mutually exclusive. So let's look at some Venn diagrams. So we have coin flips, not heads and heads. Are those mutually exclusive?
Yes.
Good. Majors, psych and history. No. I'm sorry. Yes, they are mutually exclusive. They are not complementary, but they are mutually exclusive. How about students? It's not mutually exclusive. How can we know this? I mean, we know that there are psych majors that are females, but maybe this is some problem that we're not as familiar with. Like qubits and gibberty bows. Are some qubits gibberty bows? I don't know. But if I had this diagram, and this was qubits and that was gibberty bows, what would I know? They're not mutually exclusive. So some qubits could also be gibberty bows. Right? So these are not mutually exclusive. How about this? People. So we have the people that know binary, the people that don't know binary, and we have psych majors. Is knowing binary and psych majors, are these mutually exclusive events? No. Awesome. Okay, let's talk about independence. Forget the slide for a minute. So what does it mean if you're independent?
They're not affected by
You're not affected by other people. You don't depend on someone else. So if you didn't depend on your parents, assuming that you have parents, what would that mean?
You can make choices freely. You can make choices freely.
You're making choices freely. Are you getting any money from your parents?
Unfortunately.
Then are you dependent on your parents?
Some way.
Yeah. So if you are independent of something, that means what you do or what you think or what you could buy doesn't depend on your parents. If you are getting money from your parents, you can buy more expensive things, right? So what you can do would partially depend on your parents. So events are independent when the probability of one event doesn't depend on the others. Or when the probability of one event is the same with or without the others occurring. So imagine that we flip our coin, right? And it's heads. Now we're going to flip our coin again. Assume that this is a fair coin. On the second flip, does it depend what the result of the first flip was?
No.
No. Then what does that mean? It means that flips of a fair coin are independent from one another. Right? Imagine that I wanted to pick students at random. So let's say there are like 40 students. So what's the probability that I would pick one of you guys at random, assuming that it is, truly random picking, there's no bias. 1 over 40, right? Okay, so boom, I grab you, get out of the class, go. You just say. But imagine that I told them to get out of the class. Then I wanted to pick another student at random. 1 over 39. So this is known as sampling without replacement. I am taking a sample, I'm getting rid of it, and then I'm sampling again. Now, when we sample without replacement, is each outcome independent of the others? No! Things change. The probability of you getting selected on my first statistical experiment is lower than the probability of me picking you on the last, right? If we take it to the extreme, you're the last person in the room, what's the probability that I select you? 1, right? Alright, so let's use chess pieces as an example. In the States, a lot of people talk about cards, because people are very familiar with playing cards. How many of you guys have played cards? So not all of you. How many of you guys have played chess? Not all of you. Okay. All you guys know what the different pieces are for chess, if you haven't played? Okay. I was trying to think of what game should I talk about. Should I talk about okay, or chess, or what? I think chess. So let's talk about our probability spaces in chess. We have a probability space for color, right? What's the probability space for color? There are 2 outcomes. Each are 0.5. What are the 2 outcomes? White and black, right? So our probability space, probability of black equals 5, probability of white equals 5. Right? How about the probability space for pieces?
36.
What pieces, what different pieces do we have? I was going to say, I was struggling to figure out what word I should use to describe a piece. I basically mean like the identity of the piece. Not its color, but its piece. And when I was looking online, it basically just said piece. There are 6 different types of pieces. There's the king and the queen and the bishop and the knight and the rook and the pawn, right? So 6 different pieces. And some pieces are more probable than other pieces. So which piece is the most probable if you were picking pieces at random? The pawn, right? Half of the pieces are pawns. 1/16 are king, 1/16 is queen, and then so on and so forth. Now, the question, if we want to figure out is color and piece independent of one another, then what we need to do is figure out if the probability spaces for piece or for color depend on the other thing. If we have a white piece, does that change our probability space for pieces? If we have a queen, does that change our probability space for color? If it does change the probability space, then we know that these different outcomes are not independent of one another. Does that make sense? If not, color and piece are independent. Okay, so the probability that some event occurs given some knowledge about the occurrence of other events, this is known as a conditional probability. What's the probability that this will occur given the condition of something else? Let's do a simple one. What's the probability that a heads will occur given a heads occurred?
Before you.
Maybe I should restate this differently. Not on different flips. What's the probability that a heads occurred on flip 1 given that heads occurred on flip 1? 1. Right? You already know that a flip occurred on flip 1. So with that extra piece of information, you know that the probability of the head was a 1. Alright. So what's the probability of observing a black piece if we know that our piece is a queen? If we want to represent conditional probability, we set it up like this. So P, parentheses, the thing that we're interested in the probability of, this means given, and some information. So read this as the probability of observing black given that the piece is a queen. Okay? If the probability of observing black, given that the piece is a queen, is the same thing as the probability of observing black, it means that the probability space didn't change, right? So if that's the case, then the event black is independent of the event green. So the probability space for color and piece. So already we said that the probability of black is 1/2, right? How do we know this? There are 32 pieces. There are 16 black pieces. If we assume that each of the individual objects are all equally likely, then we can just divide 16 by 32 and come up with our 1/2, right? Now, let's change the thing a little bit. So before we had probability of black, now if we have probability of black given the queen, what's that? How many? It's 1/2. Who said that? It's 1/2. How did you know that? It's what? It's
Is equal to probability of black is the same.
it is the same, but how did you know that it was the same? I mean, you need to calculate it.
There are 2 queens.
There are 2 queens, right? One of those queens is black. If we assume that both of those queens are, or that black is equally likely, I mean, you could imagine that maybe black has a different texture and people like one texture differently. But if you assume that everything else was the same except for the colors and people were truly picking at random, then we can just say 2 queens, 1 is black, 1 divided by 2 is 1/2. Oh my goodness. Those are the same. So, the event black must be independent of the event queen. Now, with chess, like, queen is just one of the values that the piece could take, right? You'd have queen, king, rook, pawn, etc. Black is just one value that the variable color could take. We can say that the variables are independent if the probability of any of the outcomes for that variable doesn't depend on the outcomes of the other variables. So, if the probability of A given B equals the probability of A, in this example we might say the probability of picking some piece given a color is the same as the probability for that piece, then those variables are independent of one another. And for the case of chess, what? Are they independent or not? They are independent. We can actually test this. I mean, it seems like they're independent, but maybe things are different. Maybe, like, people can tell the color, and maybe they're more likely to pick a white piece if we had a bag. So we could run some tests to find out. So, here's a question. Are complementary events independent? No. Good. That's excellent, right? So complementary events, this would be heads, not heads. What's the probability of getting a heads? 0.5. What's the probability of getting a heads if you know that you got a tails?
0.
0. The probability of getting a heads changed depending on whether you knew it was a heads or not. So the complementary events are not independent. How about mutually exclusive events?
They are independent.
They're independent?
Yes, maybe.
Okay, back to our psychology majors and our history majors. For this class, what's the probability of getting a psychology major? Let's say it was 0.7, right? That was about what it was. So let's say the probability of getting a psych major is 0.7. What's the probability of getting a psych major if we know that we got a history major? 0, right? Psychology and history, what are they? They are mutually exclusive. So if we know the one thing, we know that it could never be the other thing. It is dependent, that's right. So are they independent? No. How about non-mutually exclusive events? They're independent. Does anyone want to say anything else? They can be. Who said that? Kudos to you. They can be. They might be. So, talk about these, right? When we talked about color and the piece, those were not mutually exclusive. And it turned out that those were dependent or independent? Independent, yes. Does the probability of female given psychology equal the probability of female? So what's the probability of picking a random Shahir student and observing female? Maybe 0.5, right? About half of the students are males, half are females. We could look at the actual statistics for the whole population to figure out exactly what it is. But let's say it's 0.5, right? Now, if P female is 0.5, what is this? Probability of female given psychology. So we know they're a psychology major. Is there still a 0.5 probability that a random psychology major would be a female? No. Well, what's the probability? Maybe like 0.9. Maybe even higher. I don't know. It's pretty high. So here, the probability of a female changes depending on the information that you know. If it's a business student, or maybe not business, if it's an engineering student, you are less likely to observe a female. If it's a psychology student, you are more likely to observe a female. This means that majors in sex are not independent. So, the correct answer here would be maybe, or whatever you said. So, if we use the Venn diagrams to look at independence, here the coin flips, those are not independent, right? If we know one thing, then we can tell exactly what it is. With majors, we have the same thing, not independent. How about chess pieces? We've got our black pieces and our white pieces. If we look at pawns, this is not pawns. Look at this, the pawns takes up the same amount of the black as it does the white. If we were to create the kings, right, a tiny little strip for the kings, there would be just as much kings in the black as there would be in the white, which would mean that these are independent. Thank you. People, if this was the case, if this was the Venn diagram, what would you say about majors in gender, or at least the psychology major in gender? You would say that it's independent, right? This is not an accurate representation of the true state of events. But if that was the Venn diagram that you had, that's the answer you would provide, and then you might go talk to your professor and say, I think the Venn diagram is wrong. Okay, so let's talk about joint events. Is everyone cool with what we've covered so far? Awesome. So a joint event, this is like the co-occurrence of two or more events. It happens jointly, it happens together. So think about and. So a joint probability is asking about and. What's the probability of getting a queen and a black piece? Right? 1/4? No. Maybe I should say this a little bit differently. What's the probability of getting a piece that is a queen and black?
We have to imagine 1/2 plus, and then we have 1/16.
1/32, right? If we consider the colors and the pieces, we have 32 different ones, right? There's only one black queen out of those 32 pieces that you use to play the chessboard. So the probability of you observing black and queen is 1/32. Okay, this is represented by overlap in Venn diagrams. It's the intersection of two regions. This is a good way to think about it. The intersection is symbolized with this symbol here. Notice that this symbol, it looks like an N. If you can remember this, it will be much easier for you. This symbol that looks like an N means intersection. And you can think about and. The word and also has an N in it. If you spell it with a small n, that looks like that. So when you see this, think and. It's an intersection. So we have our people. We have our cool people. We have our smart people. And these two intersect, right? The intersection of cool and smart is this region right here that's dominated by sociology and psychology majors. So this is smart intersection cool. Smart and cool. Over here we have smart and hardworking, or the intersection of smart and hardworking. This, hardworking and cool, or the intersection of hardworking and cool. And psych, what is this?
Cool, smart.
It's cool and smart and hardworking, right? Or the intersection of cool, smart, and hardworking. All right, so the joint probability. This is the probability of the occurrence of two or more events, and we're going to represent it like this. So to read this, we should read probability of event 1 and event 2. Probability of male and psychology. Probability of Muslim and extroverted. Probability of teacher and awesome. Okay, so for mutually exclusive events, what would the joint probabilities be?
0.
Yes. Probability of event 1 and event 2 for mutually exclusive events is equal to 0. How about for independent events?
1. No.
0?
No.
There is nothing. Like, doesn't affect.
Actually, it does affect things. So the probability of event 1 and event 2, he said it doesn't affect things. So I think you're thinking about like the conditional probability, right? Probability of event 1 and event 2 is just the probability of event 1. Is that sort of what you're thinking?
So it's like now the probability is less. It's just when there's two independent, there's less probability.
Right, and so let's take an example to see how this works. If you don't have things like this, you might need some theory or the law of large numbers to help you out. So let's see why this is. The probability of event 1 and event 2 equals the probability of event 1 times the probability of event 2. So imagine that we have 1,000 students, right? We have 1,000 students. Now imagine that 90% have brown eyes. So what's the probability of picking a student at random and observing brown eyes?
9 over 10.
9 over 10? 0.9, right? It's 0.9. Imagine 10% are psych majors. What's the probability of picking a student at random and observing a psych major?
0.1.
0.1, that's exactly right. If we assume eye color and major are independent, what will the probability of observing a brown-eyed psych major be if we draw a student at random? That's this. So, this probability of brown-eyed and psych is equal to probability brown-eyed times probability of psych. Not 0.9, 0.09, right? Now, so we calculated this and we said it's 0.09, and that's correct. But let's try to think about this in a little bit different way. So, since probability of major equals 0.1, this means that 10% of our brown-eyed students should be psych majors, right? If they're independent, 10% of all of the students should be psych majors. 10% of the brown-eyed students should be psych majors. 10% of other things that are independent of majors. Religion. Percent of atheists that are psych majors should also be the percent of psych majors, right? So this is where the conditional probability came in. So within the brown-eyed students, 10% of them should be psych majors. If we think about the conditional probability, probability of psych given brown-eyed equals probability of psych if they're independent, and we said that these were, right? This means that 10% of our brown-eyed students are psych majors. Does everyone follow? Don't understand. Okay. So we said if things were independent, then the probability of A given B is just the probability of A, right? Now, for our example, we said that psych and eye color are independent. This means that the probability of psych given brown is equal to the probability of psych. So the probability of psych is 0.1, right? We have 1,000 students, so how many students are psych majors? Number psych is equal to 100, right? We said that 90% of our students have brown eyes. I think that's fairly reasonable in Turkey. 90% of you have brown eyes. So how many? What's the number?
90.
Number brown? Is it 90? 900, right? 90% of 1,000 is 900. Now, we said that the probability of the psych given brown is the same thing as the probability of psych. This means that, okay, we have 900 brown-eyed people. Of those 900 brown-eyed people, what percent of them are psych majors? You do know.
10%.
10%. Right? The probability of psych given brown eyes, the number of brown-eyed students, here we have the number. We know what the probability is for observing psych if we know that it's brown eyes. That's just the probability of psych. So we have 900 brown-eyed students. So how many brown-eyed psych majors do we have? 10% times 900?
90.
Brown-eyed psych. 90. It's just 10% of the brown-eyed people are psych majors, right? That's what this is. What's the percent of brown-eyed people that are psych majors? That's another way of restating that. Is that clear to everyone? We just did it. 900 times 10%, 90. So we have 90 students that are brown-eyed psychology majors. How many students are there total? 1,000. So we can divide 90 by 1,000 to get the probability of observing a brown-eyed psych major. Right? So notice that this probability is different than the probability of observing a psych major, and is also different than the probability of observing a brown-eyed person. All it is are those two probabilities multiplied by one another. Do I want to do the math? Is everyone clear? Then let's not do the math. You can look at the math if you want. All right, let's flip a coin several times, all right? What's the probability of observing the following sequence of coin flips? Heads, tails, tails, heads.
0.5 times 0.5 times 0.5.
0.5 times 0.5 times 0.5 times 0.5, right? If it's a fair coin, this outcome is independent of this outcome, which is independent of that outcome. All of these are independent of one another, right? If we have independent outcomes, all we have to do is multiply the individual multiply the probabilities of the different outcomes. 0.5 times 0.5 times 0.5 times 0.5. what this is really an intersection of things, right? Probability of getting a heads on the first intersecting with the probability of getting, or I'm sorry, tails on the second intersecting with tails on the third, intersecting with the tails on the fourth. We will not use a Venn diagram to show that out because we would need more dimensions than we have available on our board. Since the coin is fair, we can just do this, exactly what you guys said, right? Probability of heads times probability of tails, and so on. So all it is 0.5 times 0.5 times 0.5, or 0.5 to the fourth. So when all of these events are equally probable, all we have to do is just take the probability and raise it to the number of events that we have, right? Probability 0.5 to the fourth power equals 0.0625. Now let's verify our calculation. So remember, I said that an event is a collection of one or more outcomes, right? So our outcome space is just a heads or a tails. But our event space is different. We can observe different events, right? In four coin flips, we could observe 4 heads, we could observe 4 tails, we could observe head, 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 tails, 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 head, 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 tails, head, tails, tails, head, tails, and so on and so forth, right? So there are 2, 4, 6, 8, 16 different possibilities. 16 different events. Does that make sense to everyone? So basically I just did this by hand. I did do it by hand. This is a pain in the butt. This is a bad way of doing things because you have a lot of writing to do. So before we said heads, tails, tails, heads, right? How many of these events are heads, tails, tails, heads? 1, right? That's it right there. So 1 out of our 16 possible, equally probable events is the one that we were looking for. So since we know that, what can we do? 1 over 16. Wow, we get it. Yeah! So it works. Now, what's the probability of observing a sequence of 10 heads in a row? Heads, 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 however many that is.
0.5
Not over 10, pat to the 10th power. 0.5 times itself 10 times. 0.5 to the 10th power, right?
Yeah.
It's that. This would really, really suck to verify if we did it the way before, right? We're really, really likely to make a mistake. So heads, 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 heads. Okay, we can see heads, 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 tails, heads, 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 tails, heads. Oh, no! Not going to do it. We need a better way. We need a more efficient way. If you do it like this, you're really, really likely to make a simple mistake. So, let's talk about counting rules. Hooray! Counting rules. On an exam, I'm not going to say, what is counting rule number 1? So you don't need to memorize counting rule 1 is bleh. That said, I might want you to count some things. And if you know counting rule number 1, you'll be able to count them quickly. Okay? 1, 2, I was looking at this. I put Hayes up there because I was looking at counting rule number 1. And I saw that in some places this is referred to as counting rule number 2. And in other places this is not referred to as a counting rule at all. So, just know it. The total number of unique events that can occur. So, that is the total number of these different things that can occur in n statistical experiments. So here our n was 4, here it's 10, where there are k mutually exclusive outcomes. Okay, let's stop right there. K mutually exclusive outcomes. Remember when I talked about R and how it's sometimes nice to refer to numbers with a letter or a variable name? K is just the number of different outcomes that it could occur. Right? The number of different mutually exclusive outcomes. So when we're flipping a coin, what does K equal? 2. When we're talking about students in this classroom, we had history, psychology, and sociology. What does K equal? 3. If we are talking about rolling a die, K equals 6. Okay? So it's just a number of different ways you could observe, right? The number of different outcomes that you could potentially see. Anyway, if we have this, we can very quickly find out how many total different events we have by multiplying K times itself n number of times. So for a binomial outcome space, this is just 2n. So imagine that we have a coin flip, right? One coin flip. How many unique events can occur in one flip?
1, 2,
Total 1.
2 over 1?
2 power 1.
2 power 1. What does that equal? 2, right? You get heads or tails. You flip the coin twice. K is equal to
4, 2, no,
K is equal to 2.
Oh, okay, yeah.
What's equal to 4?
N, no. N equals to 2, so 2.
Right. Okay, so K is equal to 2. N is equal to 2. This is equal to 2 times 2, which is equal to 4. So if someone said 4, 4 is actually what K times N is equal to. Let's draw the event space for this, because it's not too hard. Heads, heads, tails, tails, heads, tails, tails, heads. That's it. Right? How about for 3 coin flips? What's K? 2, 3, 2 times 2 times 2 equals 8. Heads, 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 tails, 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 heads, heads, tails, 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 heads, tails, heads, tails, heads, tails, heads, heads, and heads, tails, tails. You can see that I was having difficulty doing that for 8. So if we know this rule, we can very, very quickly figure out how many different events there could be. All right, so we saw that for 4 flips. Here we had 16 different sequences. Is that right? 2 to the 4th is 8 times 2, 16. Great. So for 10 flips, we have 2 to the 10th number of different sequences, number of different events, right? So that's 1,024. Or that would be our probability. Okay, counting rule number 2. The number of unique events for n statistical experiments with K1, K2 through Kn different outcomes is K1 times K2 times whatever times Kn. This is basically just a generalized version of what we had before. When we're flipping coins, K1 was equal to 2, K2 was equal to 2, all of these other ones were equal to 2, and all we had to do was just say 2 to the n, right?
Just like in case she has this outcomes.
That's right. Sometimes maybe we don't want to just flip a coin. Maybe we want to flip a coin and roll a die, right? So the coin, we have 2, and the die is,
6.
so the total number of outcomes, let's see. So we can get a heads and a 1. Let's just say all of these are heads, okay? So all of these are heads. We can get a 1, 2, 3, 4, 5, 6. The tails. You can also get 1, 2, 3, 4, 5, 6. If we had something else, I'm trying to think of something with 3. Say we had a spinner, you know those spinners, you flick them, they're like a circle. And we've got a spinner that looks like this, there's an arrow, and then we're going to flick it. Figure out which thing it turns into. We're going to say this is 1, 2, 3. So then how many could we have? Well, K for this would be 3. So we're just going to multiply that by 3. So we could have this when it's 1. So we've got 12 of them for 1. We have 12 of them for 2. We have 12 of them for 3. 36, right? So if you know how many different ways some outcome can come out, then you can very quickly compute the number of different events that could be observed with the different outcomes by following this formula. So this is just what I did. Okay, so now let's ask a question. Which event is more probable? Observing a series of 10 heads, or observing a heads, then a tails, then a tails, then a heads, then a tails, then a heads, then a heads, then a heads, then a tails, then a tails?
Second one.
The second one is more probable. Same? How many people say same?
Oh, same.
How many people say second one?
No.
Okay. So, I'm really proud of you guys. The correct answer is same. The probability of observing this is the same as the probability of observing this. However, lots of people get this wrong. So, when I was in graduate school TAing cognitive psychology, the instructor asked this. More than half of the students got it wrong, so you guys should be proud. This is a tricky question. Both are equally probable. Why? Yes, I know they're the same, but why? I mean, saying they're the same because they're the same is not a good answer. That's right. The probability of a heads is 0.5 times 0.5 times 0.5 times... Each of these is that 0.0009, right? Same thing here. Probability of a heads 0.5 times probability of tails 0.5 times probability of tails. It's the same dang thing. So why do you think a lot of people get this wrong? You've never seen what? Because you've never seen this? Right? The probability of seeing this is really low, right? So you said you've never seen this, but yeah, but you've probably never seen this one either. So, I need something more. You're on the right track. So, there's...
Both of them are sequences and they are each unique counted and C
I completely agree with you. Each is a unique sequence that have the same probability. Each is equally probable, right? You're unlikely to see either of those when you flip a coin 10 times. But a lot of people would say the second is more probable. Yes? Not sure I followed. Did you just say that again? I'm not sure I completely understood. Let's see if my answer, if this is what you were thinking. Because it sounds like this might have been what you were saying. Like, there are lots of different ways you can get 5 heads, right? You can get 5 heads this way. You could get 5 heads in the first 5. You could get 5 heads in the last 5. You could get 5 heads in the middle. You could get, right? There are lots and lots and lots of ways you can get 5 heads. How many ways are there you can get all of them heads? So you can get 5 heads in a lot of different ways, but you can only get all heads in one way. So before we calculate how many ways we can get 5 heads, we should talk about unions. Unions are different than intersections. Intersections sounds like it starts with N, intersections, and it's represented by a symbol that looks like an N. What do you think? Unions. Unions are represented by the symbol U. It's not a U, but it looks like one. And it means union. Think or. Think or. When you had an intersection, you had an in and and, you should think and. I don't know how you're going to remember the or, but it's not an in, so don't think and. Think or. So the probability of a heads or tails. 1, right? The probability of heads and tails, 0. Right? For 1 flip. So the probability of getting a heads or a tails in 1 flip. So let's talk about some fun with unions. So for mutually exclusive events, the probability of event 1 or event 2 is just the sum of both of those probabilities, right? So for our heads and tails, probability of heads or a tails was just probability of heads, 0.5, plus probability of tails, 0.5, 1. When rolling a fair die, what's the probability of observing an even number? So an even number is a number like 2, 4, 6, 8, 10, right? There are 4 even numbers on a die, 2, 4, and 6, right? What's the probability of observing a 2? What's the probability of observing 1 over, Same thing? So this is equal to 3 over 6, which is, oh my goodness, there it is. Right? So when we have mutually exclusive events, it's really easy. All we have to do is add up the probabilities. So I said I'd mention what the third, no, I forget about that. Why add more? There's plenty here already. Okay, so for events that are not mutually exclusive, you need to be careful. So probability of cool or smart here does not equal probability of cool plus probability of smart. Why not?
Because all schools are not. Or because they have an intersection?
They have an intersection, that's right. Remember, mutually exclusive events don't have an intersection. So earlier we were saying for mutually exclusive events, this means for things that don't intersect. Cool and smart here intersect. So if we want the probability for cool and smart, what do we need to do? We need to get rid of this intersection, right? So for this, for non-mutually exclusive events, probability of cool union smart will equal probability cool plus probability smart minus probability cool intersection and smart. Yeah. How about the probability of cool or smart or hardworking? Okay, so cool, smart, or hard is going to equal probability cool plus probability smart plus probability hard minus cool and smart minus cool and hard minus smart and hard. Is that it?
No.
No!
Minus smart and hard.
Minus smart and hard, and cool. Is that right?
Yes.
No.
No, because they're including.
Because you already, decreased those, including the 3 previous ones.
Yeah.
So what we did when we got this one, we got rid of the overlap. Then here we got rid of the overlap. And then here we got rid of the overlap.
3 times weird. Sorry.
3 times.
So it's the 3 smart stuff. Smart and hard and will be added 3 times.
Plus
Plus of that.
calculations or something.
Small.
Is that right?
Plus 2.
Minus.
All right, so actually cut it. Email me the right answer for this. Okay? Before next class. You get 1 point.
Only one?
Only 1. You don't do it because of the extra credit. You do it for the learning. All right? So I'll let you guys figure that out. Okay, be careful. When we added them both together, we had this in here twice. When we subtracted this out and subtracted this out and subtracted that out, we're taking that away 3 times, right? So do we need to add it in once? I mean, we had it in there 3 times. We take it away 3 times? Do we need to add it back in 3 times, or do we need to add it once? Do it. Send me the right answer. All right. So how unions fit in with all this? So we know the probability for any set of 10 coin flips, right? So we had the heads, whatever it was. We said the probability of observing that was this. Now the question where we have how many different ways could we get 5 heads? All we need to do, since these are mutually exclusive events, each way of getting the heads is a different event that's mutually exclusive, we can just add up this probability to itself the number of times that we have. Right? So we find that number and then we add this up that many times, or just multiply that by the number that we determined. Make sense? Alright, so to get where we want to go, we want to find the number of ways that we can uniquely get 5 heads in 10 flips. To do this, we're going to have to do some other things first. First, we're going to need to figure out how many ways we can arrange 10 flips. Then we're going to see how many ways we can arrange 5 out of 10 flips. And then finally, we'll see how we can uniquely arrange those 5 of the 10 flips. Okay, so the first step is how many ways we can arrange the 10 flips. Now, the number of ways that you can order things is n factorial. This is counting rule number 3, which again, I'm not ever going to ask you, but I might ask you how to do something using counting rule number 3. All this is n factorial. If you have had math, then you know that n factorial is just the number times 1 less than the number times 2 less than the number all the way down to 1. So for something like 10 factorial, this is 10 times 9 times 8 times times 1. Right? Now, I need a better wipe off. This is so much better than the smartboard stuff. We have 10 flips, right? Flip 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many different ways can we arrange those 10 flips? 10 factorial, right? To create all of the different arrangements, we first need to pick one of the 10, right? We have a k equal to 10. So k1 equals 10. Now, we've picked the first flip. Now we have 9 more to arrange. So we said we picked 4, let's say. Notice F4 isn't in here. So we have 9 flips left that we could arrange once we've figured out the first one, right? So what is K2? Good. Now we only have 8 more to arrange. So we do this, we have 10 K for the first, 9 for the second, 8 for the third, so on and so forth. 2 for the ninth one, and 1 for the last one, right? So we can just apply the counting rule number 2, K1 times K2 times K3 times all the other Ks. And this just happens to be a factorial, right? So, regardless of whether we use counting rule 2 or 3, we get the same answer, which is n factorial or 10 factorial. This is a permutation. You should know permutation. I will not ask you what counting rule 1 is, but I probably will ask you what a permutation is. All right, let's make permutations concrete with a simple example. So how many ways can I arrange 4 students? 4 students. If we solve it numerically, what do we get? 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24, times 1 is 24. So the right answer should be 24. So here I did this last night. I have no life. Boom. They have 24 different arrangements of the 4 students. This would be like 24 different arrangements of 4 flips. Okay? So these are the permutations of 4 students. Now, getting back to our heads. We don't want to arrange all 10 of the flips. We just want to arrange 5 of them, right? So we only have 5 heads. Does the head occur on the first flip, or on the 4th flip, or on the 5th flip, right? So, if 5 of the 10 flips are heads, how many arrangements can we come up with for 5 heads in 10 flips? So, we have 10 flips to start with, right? K1 is equal to 10. What's K2? K3? K4? K5? K6? No K6. Right? We have 10 flips. We're interested in 5 of them. Right? So, how many ways could we get 5 heads? How many different arrangements of the flips could we come up with that would produce 5 heads? Right? So we're interested in 5 of them being heads. So we got 10 choices for the first, so on and so forth. But we only get down to the 5th one. After that, we really don't care. Right? Now, this is similar to n factorial, right? Very similar to n factorial. Except it doesn't go all the way down to 1 here. It stops. So, we've got 10 over 9, or I'm sorry, 10 times 9 times 8 times 7 times 6. And this is actually equivalent to this. Right? Let's do the math. All right, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 5 times 4 times 3 times 2 times 1. What does that give us? 5's cancel, 4's cancel, 3's cancel, 2's cancel, and 1's they just are. So we're left with exactly what we had before, 10 times 9 times 8 times 7 times 6, right? So, if we want to talk about things more generally, if we have n different total observations, right? N different groups, n different students, and we're only interested in ordering part of those. We're only interested in ordering R. We use the following. So, for our example, n is 10. R was what? R was 5. 10 minus 5 is 5 factorial. Not 10 minus 5 is 10 minus 5 factorial is just 5. Okay. This is going to give us the number of ways that we can arrange R of n flips. This is called an ordered combination. Ordered combinations with a simple example. How many ways could I pick 2 out of 4 students? So earlier I said how many ways can I arrange 4 students? Now I'm asking, how many ways can I arrange 2 of 4 students, right? So I could get student 1 and student 2. I could put student 2 in front of student 1, right? I can do 12 different things. So 4 factorial, this is 12 divided by 2. I'm sorry, 24 divided by 2 is equal to 12, right? So here are the 12 ways that I can pick 2 out of 4 students. This is an ordered combination, 2 out of 4. Okay, back to the heads again. So an implication of the ordered combination is that all of these things are considered different arrangements. Imagine that we get heads on the first 5 flips, right? The way we calculated things earlier, F1, F2, F3, F4, F5, is different than F1, F2, F3, F5, F4. But really, it's the same combination. We still have the same 5 flips that heads occurred on, right? So we don't care what way we order these heads. We just want to know the flips that heads occurred in, right? We want to get the unique combination of heads. So, how can we do this? Well, let's get rid of the order. When we ignored the order of the non-heads flips, that is, when we said we have 10 things and we just care about the 5 heads, we divided by n minus r, right? To get rid of the order for those other things that we weren't interested in. Now, to get rid of the order that we had in the previous, what do you think we could do? If we divided by some factorial to get rid of order before, how do you think we could get rid of order now? Let me say it again. Listen really closely to what I say. If we divided by a factorial before to get rid of order, how could we get rid of order now? If dividing by a factorial gets rid of order, how can we get rid of order? Divide by a factorial. Of what? What's the factorial going to be?
R.
R. Yeah. We have 5 heads, right? So we can arrange the 5 heads in different ways, right? Oh, we have the head over here this time. Oh, now it's over here. But really, it's still just there, right? Boom. So if we don't care about this order, since there are 5 factorial ways that we can order the 5 heads, we can get rid of that order by dividing by our factorial. Boom, there it is. This is the formula for combination. You should know the formula for a combination. This is important. So, this part on top is the number of ways that 10 outcomes could be arranged. Right? You have 10 things. We can put one out of 10 in the first, 1 out of 9 in the second, 1 out of 8, blah, 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 1 out of 1 in the 10. Then, we have the number of ways that n minus r outcomes that we're not interested in could be arranged. Right? Dividing by that, right? And we got rid of these spurious arrangements that we didn't care about. Finally, we divide by r, which is the number of ways each unique combination of flips for the 5 heads could be arranged. So what we're left with is the number of unique arrangements in which r outcomes are observed in n statistical experiments. Let's step through the process one more time. So, let's go back to our 4 students arrangement, right? So, right. Sorry, I'm jumping ahead of myself. So how many ways could I pick 2 out of 4 students without caring about order? 4 factorial divided by r, 2 factorial, times n minus r, which is also 2 factorial, that equals 6. So our unique combinations of 2 out of 4 students are these 6 here. Okay, so this is what I thought I was getting into. So we started with this, right? We've got 4 students. How many different ways can we arrange them? So we have 24 different possible arrangements that we can figure out using n factorial. Now, this is the permutations of 4 students, but we're not interested in how many ways we can arrange 4 students. Let's say I have 2 prizes that I want to give out at random. I'm just, thanks for coming to class today. I'm going to give out prizes at random. So 2 people get a prize. How many ways can I assign these 4 students to the 2 prizes? Right? Well, if I'm giving only 2 prizes away, what I can do is I don't need to worry about any of this stuff over here, right? So none of this matters. The only thing that matters is the first 2 slots that I'm filling. Now, here, notice that these 2 only differ in these last terms. But I don't care about these last terms. So these are the same. So I don't care about those since they're the same. So I get rid of them, right? Now, if you look at this, S1, S2, S2, S1. If the prizes are the same, it doesn't matter if I call you first or I call you second, right? You still get the same prize. So really, who gives a flippity-floppity floop about the ordered combinations here? Because I want to figure out the number of unique ways, not unique arrangements, but unique combinations of the 2 students. So to do this, I divide by the 2 factorial once again, and what happens is these duplicate terms, like here and here, S1, S3, where's these? One of those is going to go away. See? We're left with 6. So a synthesized example of 10 flips. So n would produce all of the following arrangements and lots more. The things in red are the differences. So these 2 are the same except for these 2. These 2 are the same except for these 2. The first parts are the same for these 4 except for those 2, which are the same. So n factorial is going to produce all of those. If we divide by n minus r, we're getting rid of all these n minus r things that we really don't care about. Okay? So that'd be like getting rid of these. By dividing by r factorial, then we're getting rid of all but the different arrangements for the things that we actually care about. So we're left with 1 unique combination. Right? We're just getting rid of everything that's not unique. So, back to our question. What's the probability of observing 5 heads in 10 flips? So we know the total number of events is 1024. We calculated that before, right? By 2 times 2 times 2, 2 to the 10th. The total number of unique ways 10 flips could result in 5 heads is the combination. So 10 factorial divided by 5 factorial times 10 minus 5 factorial, that equals 252. So if each event is equally probable, and we have 252 events of mutually exclusive events that have that probability, then what's the probability of observing the first of those events, or the second, or any of the 252 of those? Just add them all up, right? Add up the probability of the first 5 heads, the last 5 heads, the middle 5 heads, all the different orders that we came up with. So 2.52 times that 0.0009 thing. Or we could just divide 252 by 1024, right? So we do that with the unique sequences with 5 heads over the total number of unique sequences that there are. That gives us 0.24. So the probability of observing 5 heads in a series of 10 flips is almost 1/4. If we do it the other way, 252 times the probability that we came up with earlier, we get the same answer. All right, so one final example. Imagine a combo meal like your favorite fast food chain. McDonald's, what's that kebab place? Not Iskandar. Hajjol. Yeah. A combo meal, right? It comes with 3 things usually. It comes with the main thing, it comes with the side, and it comes with the drink. Now, imagine the combination of burgers, fries, and soda. Right? That's one combination. You don't have to have a burgers, fries, and soda. You can have a chicken sandwich and a chips and a milk, right? But this is one combination. Right? We can order the combination differently. We can say, I'll have a fries and a soda and a burger. I'll have a fries and a burger and a soda. But really, ultimately, it's the same combination because we don't care about the order for those individual things. Does that make sense? Well, I'm really proud of you guys. So, for review, go over this information. Next class is hypothesis testing. This class, in my opinion, was a toughie. We covered some difficult material, and we needed to do it in order to do what we're going to do next class. The next class should be easier. If you had trouble understanding this class, please come by my office hours or talk with your friends, make a study group or something, because this is important information to know. All right, see you guys later.